Hello everyone, and welcome to the Loom threading framework demonstration. My name is Michiel Frankfort and I work at a game company in Amsterdam. I was working on a real-time ray tracer and I ended up needing a threading framework to actually obtain better performance. So that's what I've built. I've built a threading framework which is built from the ground up in Unity. Allows you to use Unity objects from separate threads, focuses on distributing your workloads to multiple threads, which then of course can be executed by multiple cores. And in this particular example my framework is turned off. That's why it's so incredibly slow. So this is a flocking demonstration. If you don't know about flocking, well, you can just look it up. It's just some sort of AI behavior, very simple. And there are 7,000 particles all individually moving around and looking at each other. The average FPS is 3 FPS, which is the game FPS. The flocking behavior, which is updated asynchronically, if that's correctly English, it's running at 0.7 FPS. Now let me just turn on multithreading, if I am allowed to, because it's really slow, please. Let me just try this one more time. Alright, there we go. Now, that's a big difference, don't you think? I mean, look at those particles. They go everywhere. So first of all, instead of having 0.7 FPS on the flocking behavior update, we are now doing 2.53 FPS. And the game FPS runs at 30 FPS. So that's a big difference. So all the smooth movement comes from the main thread. The particles are displaced and updated in the main thread, where the directional where do I need to go flocking behavior update runs on 4 cores in the background. And well, you see all these nice patterns here. Let me just make sure, I mean, this is not about optimizing flocking, this is just about showing the difference between not using multithreading and using multithreading. So I hope you have a very clear understanding of the major performance difference that you can achieve even on mobile devices nowadays. I mean, this cell phone has 4 cores. This demo runs better on my phone than on my laptop. Yes, it's sad, but it's true. Oh man, this is hard to... It's so slow that actually I can't push the button. Please, just turn back on the multithreading. Well, this might even be recognized by some of you. I mean, if performance is hugged, Unity is not responsive anymore at all. So there we go. Multithreading's turned back on. Nice. Now we can do stuff. Let me just randomize some of these values. You might be familiar with flocking. If not, well, it's really cool actually to play around with. I gave them different colors. Green is separation, yellow is collision with the floor, magenta is colliding with the bounds of the world, red is collision with one of these moving bodies, and blue is cohesion. And white, no, that's not true. Alignment is blue and white is cohesion. That's it. So every particle has its own behavior. For each particle, collision is calculated with the frame, with those moving bodies, but also with themselves in the sense of separation. If they come too close, they will just try to separate from each other. And you can just randomize these values and play around with it. And I think it's pretty clear. Yeah, this is also a very nice feature. I can just tap here and they will actually get stuck to the frame. Ah, well, look at that. This is so cool. Wow, there we go. I can use my little cannonballs to shoot them off. Really epic. I like this demo. It's really fun to play around with. Even if you're not interested in flocking, or I mean in threading. It's nice to play around with flocking behavior. So that's one of the demos that I want to show you. Now, all the code, everything is included, so there are no DLLs, There's all this example project for, you could just open it up, see how I've done it. And I'm going to show you another demo, which is also included, of course, which is just a simple Gaussian texture blur. I mean, you'll probably never do it on the CPU side. I mean, yeah, you get a graphics card for this, so why would you? However, if you're ever thinking about creating your own Photoshop tool, you might end up doing this on the CPU anyways. And well, this is just, yeah, I mean, it's just blurring, nothing fancy. Just you can just set the samples and the radius, and of course everything again is run on multiple cores. You can even set the amount of threads that you want to use, the maximum. So I have 2 cores. Well, I set it to, no, that's wrong, I have 4 cores actually. And this will have major impact on the performance as well. I don't think you can actually read it. I'm very sorry, this is an old camera. Anyways, the update of the blur is around the 0.3 FPS. When I then set it to 4 cores, this will be better. There we go. 0.5, 0.6. So yeah, pretty much almost doubled, as it should, of course. And so that's another demo that shows off multi-threading. As soon as I turn it off, from the next update on, it will kick in. So there we go. And all of a sudden the FPS went to 0.1 instead of 0.5 to 0.12. And the game FPS is around the 3 FPS for the main thread, the rendering of the game. So that's again a major difference in performance. I don't think I'm even able to tap the button anymore. It's completely stuck. No, it's just, oh really, this is not nice. Ah, there we go. So next time when everything is computed, multi-core rendering should kick in again, and I can play around with my values. So that's another demonstration. It's also included into the package. And well, the nice thing about this demo is that it actually took me 2.5 hours to build. I mean, yeah, it's really easy to implement, and that's a key feature. It really helps distribute workloads to multiple thread. It will actually cut it in packages. That's how I called it. And each package will be executed by one thread, and then when everything is done, it all comes together and you will be notified with the delegate. It's very straightforward. You can also use coroutines. Just wait for the is busy flag, you know, to turn to false, and then you can continue using it. So yeah, it's all in there. So that pretty much concludes our mobile demonstration. Let me show you the web version of it. You've seen this demo before. It's the flocking demo, although in this particular case the amount of particles has been changed from 7,000 to 15,000. Same demo, same principle. You can play around with values again, although this one will have different behavior. I mean, there's a lot more particles going on. Look at that, this is really epic. So that's really cool. The reason I'm going to show you this is because, first of all, it runs in the Webplayer. I'm using Google Chrome right here. Runs really well, no problem whatsoever. And let me just show you what happens with my CPU. Because here we have the task manager and you can actually see it. Well, multi-threading is turned on, so you can actually see that I'm using almost 80%, sometimes more, sometimes less, of the CPU horsepower. This is, by the way, one really awesome behavior in the background. Wow, look at this. I played around with the values a lot, and this is, I don't know, I've never seen this one before. This is really cool. It's like a plasma beam or something. Anyways, let me just turn off threading right here. And when I do this, I will show you the difference, of course. So, okay, everything runs around 80% of my CPU load. Turn it off and instantly will drop to 25. It's still not that bad. I mean, we have an average game FPS of 3 FPS. and the flocking is updated with 2.3 FPS. So that's not a whole lot. And then when I enable it, first of all the flocking is updated. Well, you can actually see the difference here. It's no longer 2 FPS, it's around the 5-6 FPS, and the game frame rate is around 50. So that's a major difference, of course. So that's really nice. Really shows off how to what the real difference is. What I want to tell you about this is that besides all the distribution of the workload, you can still use Unity from those worker threads. This is a very common problem. As soon as you start a separate thread and you want to, for example, change the position of transform, Unity will throw errors and tell you that this is not allowed because you're using it from outside of the main thread. You might be familiar with this warning, maybe not. So that's a problem, and I've introduced a MainThread dispatcher, which is a tool that can be used in code. So for example, on one line you just change the position of a game object using this dispatcher, and then directly the next line you can already obtain this value and see that it actually has changed. Why? Because I'm actually halting the worker thread. So as soon as you dispatch it, the main thread will pick it up, execute it, no errors will be thrown by Unity, and then when everything is done, it will return to your worker thread, and you can directly access whatever you've done in the world, which is really awesome because you can even ask for a return type. So depending on the type of delegate that you use, you can actually let the action which has been dispatched return something to you, and you can use this value directly in your worker thread. So that's really nice. There's also a very solid save mode, so to speak. So every thread pool scheduler has this save mode. You can turn it on, and when it's turned on, everything will be executed within a try-catch statement, so to speak. And normally that's nice, but still nothing happens, because as soon as an error occurs in Unity, which is happening in a separate thread, it will actually be eaten by Unity. You will not see it. So the error will occur. The try-catch might prevent it from breaking the game, but still you will not be notified, even though you want to log it anyways. So that's really too bad. And this save mode actually collects all the errors and then logs it to the main thread again. So you will be notified when something within a try-catch statement goes wrong.